Where's Chubby's hat?
Oh, it was just there. Just not found. Cool.
Okay, so hello everybody. Hello. Today we're going to be doing something. Any ideas what we're doing today? Yay! So there are a lot of techniques, theorems. Yeah, inequalities is different to other parts of Olympiad math in that there's lots of specific named inequalities that you can apply onto something. By far the most common inequalities are AMGM, Cauchy, but I mean I could actually spend a lot of time on those, but I'm going to try and get through those quickly and we can get to the more fun inequalities afterwards. Sound good? So, inequalities. A basic inequality would be asking you to prove that they'll give you some variables and what values those variables are allowed to take. Usually it's positive reals, sometimes it's any real numbers. And they would ask you to prove something about those variables. And usually it'll be, they'll give you some variables and then prove that some combination of the variables, usually some sort of algebraic expression, adding, dividing, square rooting, whatever, is greater than or equal to another algebraic expression. And you need to prove that that's always true for those values. Sometimes they always also ask you, when do we actually get both sides equal to each other? For an example, possibly the first inequality you ever see if you're seeing inequalities would be you've got A and B real numbers and you're asked to prove that A squared plus B squared is greater than or equal to 2AB. Any ideas how we're going to do this?
Jensens.
What?
Jensens.
How are you going to use Jensens on that?
I think he's joking.
Like, I can figure out how to use Jensens on that, but that's just unnecessary. Like, you need to do like cases where A and B are positive and negative, and it's not nice. Okay, so the easiest way to do this, yes? Like I said, you're going to need to do cases if you're going to do like Merhead. Remember, Merhead initially, it only works for positive real numbers. Here we have arbitrary reals. So we also need to take care of the fact that A and B could be negative. Okay, so easiest way to do this is you take the 2AB to the other side and you want to prove, so it's equivalent to A squared minus 2AB plus B squared is greater than or equal to 0. If your school teachers are any good in any way, shape or form, you should be able to recognize what this is. That is simply A minus B squared greater than or equal to 0. And that is the first fact about inequalities. Anything squared is always non-negative.
In the reals.
In the reals. It's very rare that you have an inequality that has to do with stuff that's outside of the real numbers. But yes. So in the square of any real number is greater than or equal to 0. And that is almost the basis of every other inequality you can come up with. Almost all of them just build up from this. Okay. So that's the first important fact. Any square is always greater than or equal to 0, and equality if and only if x is actually 0. So equality if and only if x is equal to 0. That's the first one. This is a sort of a special one in that it works no matter whether a are positive or negative. Most named inequalities only work with positive integers, or not positive real numbers, because with positive reals you can do things like square rooting and taking arbitrary powers of positive real numbers that you can't do with negative numbers. So, as a next case, slightly more complicated, we're going to do this next example in like 5 different ways. Yay. So, A, B, and C are, let's make them positive this time. And prove A squared, B squared, C squared is greater than or equal to AB plus BC plus CA. Okay, first way to do this is to build it up from the previous example. And inequalities, you often have to build up smaller ones and then get to bigger inequalities. So a squared plus b squared is greater than or equal to 2ab. Same for b and c, and c and a. If you add them all together, what you get is that 2a squared 2b squared plus 2c squared is greater than or equal to 2ab, 2ac, 2cb. And then you can just divide by 2 on each side. Good. Perhaps important to notice is that you cannot generally subtract inequalities. You can add inequalities that are facing the same direction. And obviously if you multiply an inequality by a negative number, the sign changes. But you cannot subtract inequalities, because if you subtract 2 positive real numbers, you can get any positive or negative real number. So please, I don't want to see in any of your tests having one inequality and subtracting another one. Just don't do that, please, ever. Okay, so that's one way to do it. Let's take suggestions from the audience. What's another way to do this? Cauchy-Schwarz. Okay. So the next one is a result called Cauchy-Schwarz inequality. And what Cauchy-Schwarz says is that given two finite sequences of real numbers, technically infinite sequences works as well, but 2 finite sequences of real numbers, a1 to an, of the same length, b1 to bn, the following is true. If I take the sum of the a squareds times the sum of the bi's squared, that is greater than or equal to having the pairwise product. So a1 goes with b1, a2 goes with b2, up until an going with bn, that all squared. That is Cauchy-Schwarz inequality. And The equality case here is a bit special. So equality happens if and only if one of the sequences, let's say A1 up to AN, is some multiple of the other one, B1 up until Bn. Either A is a multiple of B, or the sequence B is a multiple of A. So they all have the same ratio. And often with these general inequalities, you have some, like here we have 2n variables to work with. The key to being able to do inequalities is to figure out what goes in the place of each of those variables. In this case, we're going to apply it to solve this inequality. We have that, where should I do it? Let's do it over here.
Can I just ask quickly? So Cauchy-Schwarz has been proved a long time and you just proved it now?
Yes. It was proven many times by different people. And some, like if you check the Wikipedia article, some people call it the Cauchy inequality, some people call it the Schwarz, some people call it Cauchy-Schwarz, some people call it Bunyakovsky's inequality. There's like 2 or 3 other names that's also attached to it. So, how we're going to apply this? A squared plus B squared plus C squared multiplied by B squared, C squared, and A squared. So here our N is 3, our one sequence is ABC, the other sequence is BCA. Cauchy-Schwarz tells us that's greater than or equal to the pairwise product, so A goes with B, B goes with C, C goes with A, all squared. And obviously the top is equal to A squared plus B squared plus C squared squared. Now, I have that one number, non-negative number, because those are all squares. If you add squares, it's still non-negative. One number squared is greater than or equal to another number squared. Can I then say that the inside number is greater than or equal to that one?
Not yet.
It's not negative, so
Yeah, it's not negative.
Yeah, because the first one is non-negative. Okay, in general, what I can say is that the square root of the one side, even if the inside is not non-negative, is greater than or equal to the square root of the other side. And the square root of a square is what? The original thing?
Yeah, it's
The absolute value of the original thing. And because this left-hand side, the inside is non-negative, I can take away the absolute values, but I don't yet know that the inside of the right-hand side is non-negative. But the absolute value is always greater than or equal to the thing inside it. Okay, that is Cauchy-Schwarz inequality. Next suggestion. Rearrangement. Excellent. Excellent suggestion, my good sir. Now, the rearrangement inequality again deals with 2 sequences, A1 to AN, B1 to BN, subject to specific conditions. So the A1s have to be non-increasing, and the BNs also have to be non-increasing. And we also need a permutation of the numbers from 1 to n. So sigma a permutation of the numbers 1 to n. And then what this says is that if I look at the product, let's say A1 multiplied with the permuted, so we're going to, BI's initially start out in decreasing order. We're going to permute the BI's in according to the sigma permutation. So A1 is going to be multiplied with B of sigma 1. A2 is going to be multiplied with B of sigma 2. And AN with B of sigma n. So we're actually permuting the B1 up to Bn and then forming the pairwise product of each of them and adding up. And the question is, over all these permutations, which of these sums is going to be the greatest? And the answer is, when the permutation sigma is the one that sends 1 to 1, 2 to 2, up until n to n. So this is less than or equal to A1 being multiplied with B1, A2 being multiplied with B2, up until AN multiplied with Bn. And among all these permutations, the least possible value that it can have is when sigma, the permutation, is in the reverse order. When A1 multiplies with Bn, A2 with Bn minus 1, up until An with B1. So if you want to make this sum of products the greatest, you multiply the biggest A with the biggest B, second biggest A with the second biggest B, and so on up until the smallest A with the smallest B. That's the rearrangement inequality in all its glory.
What's the equality case for?
It's complicated. Okay. So, how do we apply it to this case? As before, we are going to assume this is symmetric in A, B, and C. If we swap any two of A, B, and C around, both sides still stay the same. So we can, without loss of generality, assume that A is greater than or equal to B, greater than or equal to C. And then, as in the Cauchy-Schwarz case, our sequence A and our sequence B is both going to be the sequence ABC. Then rearrangement tells us that, first of all, if I multiply A with the biggest of the other sequence, we have two sequences, one ABC, the other one also ABC. A with A, B with B, C with C, that is greater than or equal to. And now the second sequence B's, I'm going to permute. So instead of ABC, it's going to be BCA. And I have AB, BC, and CA. And the left-hand side is obviously A squared plus B squared plus C squared. And that's how you can use the rearrangement inequality on this one. Okay. So far we've done 3. Another suggestion? Sorry, what? Mirrorhead. Okay. Should we really do Mirrorhead before like AMGM or something? I mean, yeah, Mirrorhead's gonna be a killer one to write down. But okay, I'll do AMGM since it's actually much more common and useful. So, AMGM inequality. Here you have one sequence of numbers, and these have to all be non-negative. A1, A2 to AN being greater than or equal to 0. And what the AMGM inequality says is that if you take the arithmetic mean, that's where AM comes from, to AN, add them all up, divide by n. That's one way of forming, like getting some sort of average of the numbers. That is greater than or equal to the geometric mean, which is multiplying all of them and taking the nth root. Both of these are different ways of sort of getting an average of the numbers, and this average is always greater than or equal to this average. Arithmetic mean, geometric mean. There are also other averages. So I'm going to extend this a bit. QM, AM, GM, HM. All of these actually fall under a more general thing called the power mean inequality, but I'll just write down these for now because they are the most useful. This is less than or equal to taking the squares of all of them over n. So this is some sort of average of the square value. So to get it back to the level of a's, I have to take the square root of that. And the, the harmonic mean on this side, well, we take 1 over a, 1 over a2. So we take the average of 1 over each of them. And then this is an average of 1 over the a's. So to get back to the level of a's, we take 1 over that. Most common is the one in between. The arithmetic mean of any n is greater than or equal to the geometric mean of those, but the others are also quite useful too. In particular, the AMGM applied on two variables may look familiar. If I apply the AMGM on a squared and b squared over 2. So now our a1 and a2 are a squared and b squared. That is greater than or equal to the geometric mean, so the square root of a squared times b squared. And because a and b and c are positive, this on the right hand side is just ab. And I can do the same thing for BC and CA. And then if I add them, I get a squared, b squared, c squared, ab, bc, ca. Okay, so that is the AMGM. One last suggestion. Could do Mirrorhead. Any other requests? Mirrorhead it is. Okay.
You could use Newton.
Actually, I think Newton is... Who gave you that suggestion? Oh, you did? Okay, no, that's good, that's good. I think Newton is actually more interesting, especially since we were introduced to the elementary symmetric polynomials yesterday. So, you guys remember the elementary symmetric polynomials? If you have n variables, you take the product of I of them at a time, and you take all possible products of those, and that's your elementary symmetric polynomial. So what Newton's inequality on elementary symmetric polynomials says So let's say I have a1 to an. These can be any real numbers, not necessarily non-negative. And I, or should I use I? I'll use r. R is some number between 1 and n minus 1. And what Newton's inequality says is that the rth symmetric polynomial. Do you need a reminder of what that is, or should I just write down sigma r? Okay. Sigma r of the a1s to an's is, okay, shortest way I know of, it's the coefficient of y to the r in the product, 1 plus a1y. So the product, 1 plus a1y, 1 plus a2y, all multiplied up until 1 plus a n y. But it's also just the sum of all product of r of these variables at a time. So, how many terms are there in sigma r? If I have n variables and I'm choosing r of them at a time, how many terms do I get? N choose r. So if I want the average of these sums of r of them at a time, I would say sigma r divided by n choose r. That's sort of an average of them. And what Newton's inequality says is that that squared is greater than or equal to sigma r minus 1, n choose r minus 1. Again, another average, but just with the previous value of r, multiplied by sigma r plus 1 over n choose r plus 1. Same average with the next value of r. That is Newton's inequality. That is a thing of beauty right there. Okay. So in particular, if I have three variables, a, b, and c, and my r is 1. So let's say I have variables a, b, and c, and r equals 1. What this says is, okay, first of all, sigma 1 over n choose, n is 3, so sigma 1 over 3 choose 1 squared. I have sigma 0 over 3 choose 0, and sigma 2 over 3 choose 2. Okay, what's sigma 1? Remember from yesterday? You just add together all of them one at a time. So here we have a plus b plus c divided by 3 choose 1 is 3 squared is greater than or equal to, what's sigma 0?
It's just 1, I think.
Just 1 over 3 choose 1, which is, sorry, 3 choose 0, which is 1. Sigma 2 is the product of two of them at a time. That's AB, BC, and CA over 3 choose 2, which is 3. So, we just multiply each side, simplify, and see what we get. We're also going to multiply by 9 on each side to get rid of the 9 that we're going to have in the denominator over here. So on this side we'll have a squared, b squared, c squared, ab, bc, ca On the other side, the 9 that we multiplied by is going to cancel with the 3 there. We're still going to have 1 3 left. We have AB plus BC plus CA common on each side. So we're taking away 2 of that. On the left-hand side, we're left with A squared plus B squared plus C squared. On the right-hand side, AB plus BC plus CA. Also, fun story. I was in the IMC a few years ago. Not the school IMC, the university level IMC, International Maths Competition in Bulgaria. And one of the questions in the paper was literally Newton's inequality for general N for R equals 3, I think. So I just said this is Newton's inequality. Got full marks for it. Yep.
So if you can do that, then why can't you say that 1 to the 8 cube pi?
Well, okay, technically the form that it was in, okay, remember yesterday I said that there are these elementary symmetric polynomials, and then there are the other ones which are just the sum of kth powers at a time. The form they gave it in was in terms of sums of kth powers. So I first had to convert all of that. Once it all simplified, it was just Newton. Then I could say, okay, this is Newton. Whereas, yeah, doing it with Q5 today, it was literally just that theorem. Okay. Good, good, good. Let's see if there should be some nice problems that I can show you how to do. Okay, how about this one? We have x, y, and z are positive real numbers, and what we're asked to do, in fact any real numbers, not necessarily positive, and what we're asked to do is find the maximum value of the following expression: 3x, 4y, 5z over x squared plus y squared plus z squared square rooted. Okay. Ideas? No? I mean, no. Just no. Any other suggestions? One of these that we've done already. Yes?
You just have to choose one of those and you use that constant what's in it.
No, you don't use it. You just use Cauchy-Schwarz.
Yeah, you just use Cauchy-Schwarz for this one. So, Cauchy-Schwarz, first of all, we need to find out what our two sequences are. Here we have a sum of squares, so this could be one of the brackets in the Cauchy-Schwarz expression. Here we have a pairwise product with some of the terms that are squared here below. And it actually tells us what the terms of the other sequence are, 3, 4, and 5. So, if we do x squared, y squared, z squared, times 3 squared, 4 squared, 5 squared that is greater than or equal to 3x, 4y, 5z squared. So let's divide by this sum of squares to get it at the bottom like we wanted. On the left hand side we'll have 3 squared plus 4 squared plus 5 squared, which is 50. On the other side, that. Okay. So now we can take the square root of each side. The square root of 50 is greater than or equal to, so the square, when we square root it, becomes an absolute value because we don't know whether the thing inside is positive or negative. Over the square root at the bottom. And of course, this absolute value is greater than or equal to the thing itself. Okay. When do we have equality here? So, okay, actually we haven't quite finished yet. We've shown that this fraction that we're given is less than or equal to square root of 50. We've shown that that's less than or equal to that, but we haven't shown that it's the maximum. Maximum means that you actually have to have some point where it's equal to it. So we need to find 3 values x, y, and z where this fraction is actually equal to square root of 50. Yeah, we can do 3, 4, and 5 because the equality case for Cauchy-Schwarz is that one of the sequences has to be a multiple of the other. You could have a multiple with the ratio just 1. So we can say that equality occurs when x equals 3, y equals 4, and z equals 5. As one example. That's not the only case where that equality occurs. Yes?
We actually need to evaluate the example. Can I just say that Cauchy-Schwarz says there is an equality yet, since we've only done division and
yes, so yeah. So we can just say Cauchy-Schwarz gives us equality. Well, Cauchy-Schwarz gives us equality over here. We just still need to check that this side here is still an equality. So yeah, Cauchy-Schwarz gives us this part here, that part we need to take care of. For example, if we chose -3, -4, -5, then it wouldn't have worked. Okay. So that's one. Should we do Muirhead? Or Jensen's? Or Karamata's inequality? Okay. So first of all, before we can do Muirhead or Karamata, what we need is the idea of one sequence majorizing another. So here we can have any two sequences. Give me a letter.
A.
A, no. More suggestions?
J.
J, no. H. How about non-Latin letters?
Alpha.
What? Alpha. Okay, let's do alpha. So let's say we have two sequences, alpha 1 up to alpha n, and we're going to use a weird notation sort of like a greater than sign, and beta 1 up to beta n. This is majorization. What this means is that, well, three conditions. First of all, the A's are in decreasing order. Second of all, the B's are in decreasing order. And the final one, which is really what the majorization means, is actually a group of several conditions. A1 is greater than or equal to B1. And if you sum the first two of A, that's greater than or equal to the same for B. If you sum the first three, that's the same for B. And continuing on, up until n minus 1, but the last case, you have to have equality. So if you actually add all of the A's, that has to be equal to all of the B's. So you can't just have each corresponding A bigger than each corresponding B. So in a sense, what majorization means, since they both have the same average, is that the B's are closer together on average. The A's are more spread out. That's essentially what majorization means. Now, there are two main inequalities that are true when you have a majorizing sequence, or one sequence majorizing another. And the first one I think I'll do is Merhead. So, for Merhead, you need one sequence, alphas, one sequence, betas, one of which alphas majorizes the betas. And you also need a sequence of non-negative, but let's say positive real numbers. First of all, I'm going to define a particular sum, which is a very big sum. I'm going to say, let's say mx of alpha is going to be the sum over all permutations of the numbers from 1 to n. So we're going to have lots of permutations. In fact, I'm going to sum over all possible permutations. The sum of x1 to the power of alpha sigma 1, x2 to the alpha sigma 2, up until xn to the alpha sigma n. So one way to see it is that, let's say you have x, y, and z. So that's a definition. Example, if you have m of, and you have 3 variables, x, y, z, and your sequence is, alpha is 2, 1, 0, for example, then the sum is going to be x to the power of 2, y1, z0, plus x2, y0, z1. So the exponents are permuted and we sum over all possible permutations. Okay. That is the Merhead sum. Now what Merhead says, the Merhead's inequality, is that if you have a sequence alpha which majorizes a sequence beta, then the first sum with alpha, so we have the same bases, the same sequence that's going to be the bases of this big exponent sum. If you have the elements of alpha dancing around on the exponents, that is greater than or equal to the same sum with the elements of beta instead. And that is Merhead's inequality. Yes?
The alpha and betas, are those any reals?
Any reals.
And it can the xi be 0? Like,
They can be 0. Let's keep them positive.
You know, if there were,
yeah, for 0, you just don't have to worry about it.
Yeah, if it's a 0, you might have to worry about a negative exponent. Okay, so this is Merhead's inequality. Let's apply it, shall we? So let's say we've got 3 variables, A, B, and C. And our one sequence alpha is going to be 2, 0, 0. Beta is going to be 1, 1, 0. But in decreasing order, the sum on each side is 2, so it's the same. 2 is greater than or equal to 1, check. 2 plus 0 is greater than or equal to 1 plus 1, check. And the sums are the same, so this does majorize this. And if we write down what Merhead's inequality says, we will have x to the power of 2 plus another x to the power of 2. So I'm just going to say 2 times x to the power of 2, sorry, a to the power of 2. Is greater than or equal to. On this side, we'll have a to the 1 times b to the 1 times c, and we'll have that term actually happening twice because 1 and 1 can be swapped around. So we'll have 2ab, 2bc, and 2ca. Look familiar?
it's the thing.
It's the thing. Yes, it is the thing.
Wow. It's like that.
Okay, the next inequality that makes use of majorization is called Karamata's inequality. Before Karamata, I'm going to do another one called Jensen's inequality as an introduction. First of all, for Jensen's inequality, we need something called a convex function. So let's say you've got a function from an interval, a, b, to the real numbers. Actually, you might have seen convex functions in school, but I'll write down a definition here for completeness. So that function is convex if and only if, whenever, let's say you have 2 points in this interval, if x and y are in this interval, and you have some number between 0 and 1, let's say t, then the following holds. So t f of x and 1 minus t f of y is greater than or equal to f of that. Okay. What this condition means is that, okay, let's draw a graph of our convex function. Let's say x is over there, y is over there. This is f of y, that is f of x. Now this linear combination, tx plus 1 minus ty, when t is 1, this is at x, and as t grows from 1 to 0, it becomes y. So this linear combination, tx plus 1 minus ty, is somewhere in between x and y. The corresponding value of f, so this is the right hand side, this value of f. F of tx plus 1 minus ty. We have the same linear combination with t and 1 minus t on the left hand side, except it's on the outside of the f's. So it's a linear combination of the function values. And what that is if we draw a line between f of x and f of y, it's that value on the line. As t moves between 0 and 1, we move along this line over here. So that value has to be greater than the value on the curve. Since this is true for every pair of points, it means that if you draw a line between 2 points, every point on that line has to be above the curve. What that generally means is that your function bends upwards. Well, not necessarily upwards, but it bends convexly, for lack of a better word. It doesn't necessarily have to go upwards. You could have a function going like that, which is still convex, but it doesn't go upwards. So that is what a convex function is.
And it's going the other way. Like if it's upside down.
Yeah, if it's upside down, it's concave.
And if inequality, how does it change?
So it's concave if this greater than or equal to sign is always the other way, always less than or equal to. Okay, how do we tell if a function is convex or concave? There are some examples of convex functions, and if you add two convex functions or multiply it by a positive real number, you get another convex function. So some examples of convex functions are powers of x. You also have, actually x powers. You also have powers of x. You have...
Is that for the second one? Is that for x positive?
Yes, the second one is for x positive. See, what else do we have? If you shift a function to the left or to the right, it still stays convex. Or in general, if you have f of some linear combination of a that, then that is also convex if f of x is convex. And so on. Lots of but in general, if you have another function that is, you want to know if it's convex or not, if you know calculus, then f is convex And assuming your function is differentiable, it's convex if and only if the derivative is increasing or non-decreasing at least. If you want to take it further, if your f prime is not too bad and you're okay with differentiating again, if only if f double prime is always greater than or equal to 0 in whatever interval you're working in. Now, if you have a convex function, you can then do Jensen's inequality. So if your a1 to, actually let's say x1 to xn are in your interval, and f is convex in that interval, then Jensen's inequality says if we take the average of the f values that is greater than or equal to f of the average value. Okay, that is Jensen's.
Can you use this on an open interval?
Yes. Okay, and the last one, you need one sequence majorizing another one. So this is actually a sequence of length n majorizing another sequence of length n. And Karamata's inequality says that if you add the function values of the one sequence, that is greater than or equal to the same thing for the other. Okay, that's Jensen's and that's Karamata's inequality. Yes, only if f is convex, yes. Okay. I have maybe like 2 or 3 minutes left. Do we have any more questions? Yes.
So if we were given this, like, would we be asked to, we have to show that it majorizes it, or would we be given that?
Yeah, you would most likely have to prove that whatever sequence you're dealing with majorizes the other sequence. Any last questions? No? Last thing I would mention, if f is convex, then that's going to equal to that. If f is concave, then the inequality just switches around. And same thing for Karamata, just switches around. I think that's it for me. I mean, in a way, it becomes even easier to do the Jensen's. Yeah, the issue is just proving that log is concave. Yeah.